In the following, we have this example. This Banach algebra of all continuous function on omega is semi-simple by the previous proposition, and also we have a notation but we have this proposition let me recall this notation because we need to sum definitions such as f of e, the set of all finite rank operator. Okay, notation for a Banach space E and for x0 in E. So this E is a Banach space except belong to E, and lambda x0 belong to E, and lambda 0 belong to the dual of E. We define x0 tensor lambda 0 in B of E, the set of all bounded linear operator from E to E. Okay, by this function maps x to this. Please note that the action of lambda 0 on x is an scalar. Okay, so that this multiplication is an element of E because we assume that x0 is an element of E, so that this is an element of E, and so this is an element, a function from E to E. Let me write this again for you. Okay, let's be a Banach space x0 belong to E and lambda be in the dual of E, E prime or E star. We define this function from E to E by this function rules. For each x in E, we define this function on E. Okay, on x equal to the act of lambda 0 on x multiplied by x0. This is an scalar number. Okay, so that this is an element of E. This maps shows that given x0 and y0 in non-zero element of E, there exists a bounded linear operator from E to E such that S of x0 equal to y0. S of x0 equal to y0 because if x0 and y0 is two non-zero elements in E, then there exists S in B of E such that S of x0 equal to y0. And this is trivial because if we consider if lambda 0 in A prime is a function with this property that lambda 0 on x0 equal to 1, then for S equal to y0 tensor lambda 0, we have S of x0 equal to y0 tensor lambda 0 on x0, and this is equal to lambda 0 on x0 multiplied by y0, and this is equal to y0 because this is equal to 1. Okay, so that we find this bounded linear operator with this property. Okay. And please note that this function x0 tensor lambda is an element of B of E, because at the first we see that this is linear for any x and y in E, and for any alpha in complex numbers we see that x0 tensor lambda of alpha x plus y equal to lambda on these vectors alpha x plus y multiplied by x0, and this is because lambda is an element of the dual of E, so that this is linear. This is equal to alpha lambda of x plus lambda of y, this multiplied by x0, and this is equal to alpha lambda of x multiplied by x0 plus lambda of y multiplied by x0, and this is equal to x0 tensor lambda of x and also this alpha must be right plus x0 tensor lambda of y. Okay, so that this is a bounded, sorry, this is a linear function, so this is linear and also for any x in E with this property that if x belongs to E and the norm of x is less than 1, less than or equal 1, then this, multiplied by x0. And this is why this function rose, okay? So that the norm of this in E, okay, equal to this norm. And this is equal to the absolute value of this, because this is a complex number, okay, multiplied by the norm of x0. And we know that this norm is less than or equal 1, so that this is less than or equal the norm of lambda, the operator norm, okay? So that this is less than or equal the operator norm of lambda multiplied by the norm of x0. So this operator is bounded and the operator norm of this is less than or equal the operator norm of lambda multiplied by the operator norm of x0. So this is important, that this function belong to B of E, okay? And operator T in B of E is finite rank if its range T of E is a finite dimensional vector space, okay? If T belongs to B of E, you know that if T belongs to B of E, then T is a bounded and linear function from E to E, and so T of E is a subspace of E, and E is a vector space and T of E is a vector space. Now if this is a finite rank vector space, we say that T is a finite rank, okay, if T of E is a finite rank in E, okay, finite rank, finite dimensional vector space or linear space. vector space or linear space, then T is called a finite rank operator. Finite rank operator. Each finite rank operator is a linear combination of rank 1 operator of the form x0 tensor lambda, and this is very important. It is very trivial that this is a finite rank operator, okay? x0 tensor lambda is an operator with the rank 1 because it is very trivial, because the image of this linear function equal to the set of all x0 tensor lambda of x such that x belong to E, and this is equal to the set of all elements by this form, okay? X belong to E, and we know that this is scalar numbers, so that this is equal to the space generated by x0, okay? And this is a vector space by dimensional 1, so that this operator is an operator with rank 1 because the dimension of the image of this operator is 1, okay? Now any finite rank operator is a linear combination of operator with rank 1 with this format, and the collection of finite rank operator on E is denoted by f of E, the set of all finite rank operator of E, so that f of E is a subspace of B of E, and this is clearly an ideal in B of E. Okay, which is trivial that f of E is an ideal in B of E, because if, for example, T belong to f of a to be a finite rank operator from E to E, and S be a bounded linear operator from E to E, then TOF of A, TOS of A is a subset of or equal to T of S of E, okay, and this is a subset of T of E, and we know that this is a finite dimensional vector space. This is a finite dimensional vector space. So TOS of E is a finite dimensional vector space or linear space, okay, because T of E is finite dimensional. Any subspace of a finite dimensional vector space is a finite dimensional vector space. And also from these assumptions we can conclude that SOT of E or S of T of E is a finite dimension vector space. And this is very trivial because that this is a finite dimensional. We know that the image of any finite dimensional vector space is a finite dimensional vector space. This is finite dimensional, so that this image must be finite dimensional vector space. So that for any T in F of E and for any S in B of E, we see that TOS is finite, and let me write in the bottom. So TOS and SOT are finite dimension linear space, and this shows that this is an ideal, okay, in B of E. We have this proposition Let E be a non-zero Banach space, then B of E is semi-simple. This proof is very trivial. Dear students, do you have my voice? Okay. Let E be a non-zero Banach space, then B of E is semi-simple. Semi-simple. Proof. Take T non-zero element in B of E. Then there exists x0 and y0 in E minus 0 with this property. We prove this, okay? Now choose another element of B of E with this property. Then clearly we have IE minus ST of x0 equal to 0. It is very trivial because IE minus ST IT sorry IE minus ST of x0 equal to IE of x0 minus ST of x0, and this is equal to x0 because this is the identity map, minus S of T of x0. But T of x0 equal to y0, so that this is equal x0 minus S of y0, and this is equal to x0. This is x0 minus x0, and this is equal to 0. Okay, and so this is not invertible element, hence T not belong in the radical of B of E. We see that if T belong to the radical space of B of E for any S, this must be invertible, okay? So this shows that T cannot belong to the radical space of B of E, so that any non-zero element cannot belong to this radical, so that this radical equal to 0 only. Let me 1 minute. Okay, so we have this easy proposition. However, the algebra B of E contains many non-zero nilpotent operators, and hence the radical space of B of E is not equal to the quasi-nilpotent element in B of E, because you know that any nilpotent element is quasi-nilpotent, okay? And we have the definition of compact operator. Let it be a Banach space, and operator T in B of B is compact if the closure of the range of E1 is compact. When E1 denotes the closed unit ball of E, okay? So that the definition of compact operator can be right by this definition. G in B of E is called compact operator if this closure be finite. T of a set of all x in E such that the norm of x is less than or equal 1. Okay, this closure is compact. And in book denoted this by E1, okay, or E1 in this closure. The collection of all compact operators denoted by K of E, and this is a closed ideal in B of E again, and this is easy to check, and clearly F of E is a subspace of K of E. Okay, please write the proof of these two observations. The collection of K of E of compact operator is closed, and this, look, let me write this for you. يرجي إثبات هذين كتدريبات. okay, this and this. The closure of F of E denoted by A of E is called approximate operator. Okay, and this is an ideal of B of E again. This is called the space of approximable operator. For many Banach spaces we have this equality, A of E equal to K of E. But Banach space E such that we have this asterisk inclusion are known. Okay. And at the end of this section we have this theorem. Let E be an infinite dimensional Banach space, and suppose that T belongs to K of E, so that this is a compact operator. Then sigma of T is a countable compact set of the form Zn such that n belong to n include 0, where this is either finite or a sequence which converges to 0. Okay, the limit of Zn tend to 0. Okay, the limit of Zn equal to 0, or this set be finite. Each z in sigma of t minus 0 is an eigenvalue of t, and the corresponding eigenspace is finite dimensional space. And for each z non-zero complex number, this subspace is closed in E, and we have this equality, this dimension equal to the dimension of this space. This proof is very nice, but this book omit this proof, so that in particular this is surjective if and only if it is injective. This function is surjective if and only if this function be injective, because this function is injective if and only if this kernel will equal to 0. Okay, 0 only, so that this must be the dimension of this space must be 0, and so that this quotient space must be trivial, and so this equal to whole of E. Okay, and we have this proposition. Please prove this theorem or this exercises 1, 2, 5 and 7. Okay, يرجي حل التمارين 1, 2, 5 and 7. Okay, okay, and we have this additional note, and next we have Gelfand theory. Let me begin this section and continue tomorrow inshallah. Definition: let A be an algebra. A character on A is an epimorphism from A to C. Epimorphism is meaning onto homomorphism. Okay, so that this phi must be linear functional, because the range of this homomorphism is complex number. This is a linear functional, and this linear functional must be multiplicative, and also must be epimorphism or onto or surjective. Okay, this function must be surjective or onto. Characters are sometimes called multiplicative linear functional, so that this phi is a multiplicative linear functional. Okay, and we write phi of A for the set of all characters on A, or the set of all multiplicative linear functional from A to C. From A to C. Phi of A is called the character space of A. If A has an identity such as EA, then clearly phi of EA must be equal to 1 for any phi in phi A. And this is very trivial, because if phi belong to phi of A, then phi of E of A equal to phi of EA multiplied by EA, and this is equal to phi of EA multiplied by phi of EA. And we know that this is a complex numbers. Please note that phi is a linear functional from A to C, so that these are complex numbers, and this shows that phi of EA must be equal to 1. Example, let A equal to C of omega and epsilon x0 of f equal to f of x0 for any f in this Banach algebra. Then this is an element of phi of A, or this is a bounded and linear functional, that is multiplicative. Because if f and g belong to C of omega, for example, epsilon x0 of f plus g equal to f plus g of x0 by this function rules. F plus g of x0, and this is equal to f of x0 plus g of x0, and this is equal to epsilon x0 of f plus epsilon x0 of g, and also epsilon x0 of fg equal to fg of x0, and this is equal to f of x0 multiplied by g of x0, and this is equal to epsilon x0 of f multiplied by epsilon x0 of g. So that this is linear and this is multiplicative. And also if we consider an scalar such as alpha, okay, is alpha multiplied in this first part, so that this is a linear function and this is a multiplicative function. So this must be belong to the spectrum space of C of omega. This is an example, okay? And we have a very nice corresponding any character corresponding to a maximal ideal in A. Let A be an algebra and let phi belong to phi A. We write m of phi equal to the kernel of phi, the set of all A in A, such that phi of A equal to 0. Then we have this proposition, let A be a unital algebra, then this map is a bijective from phi of A onto the set of all maximal ideal of codimensional 1. Clearly each m phi is a maximal ideal of codimensional 1. Okay, if phi belong to phi of A, then m phi, or the set of all x in A, such that phi of x equal to 0 is a maximal ideal in A with codimensional one or codimension 1. Okay, This is one codimensional, or could have a codimension 1. And its proof is easy because for any B in A, if let B belong to E, okay, if phi of B equal to alpha. Please note that alpha is a complex number because phi is a linear functional from A to C, okay? Then we see that phi of B minus alpha EA equal to phi of B minus alpha phi of EA, and phi of EA equal to 1, so that this is equal to alpha, and also phi of B equal to alpha, so that this is equal to alpha minus alpha, and this is equal to 0. So B minus alpha EA is an element of the kernel of phi. Kernel of phi, and this is denoted by M of phi. Okay? And consequently, B is an element of EA plus the kernel of phi, or EA plus M phi. And this be considered arbitrary, hence we have this conclusion that this is a one-dimensional vector space. For any B in A, B plus M phi is an element of this space, okay? So A multiplied by M phi is a one-dimensional vector space, and so, or equivalently, M phi is a one codimensional space and this shows that phi is a maximal ideal. It is very trivial that M is maximal ideal if and only if it is a codimensional 1 space, okay? Is hold for any ideal. And also, so that we have this for any phi in phi of A, and phi is a maximal ideal with codimensional y, so codimensional 1. And also any because we must prove that this is a bijection, okay? Please note that for any maximal ideal, conversely, let me write this sentence. So the map, this map, phi to n phi, phi maps to n phi from phi of A to the set of all maximal ideal, all M, such that M is a maximal ideal in A, okay, is well defined. Now we prove that this map is onto we will prove that this map is onto. For this, let's M be maximal ideal in A. Then J equal to the set of all x plus lambda EA such that x belong to M and lambda belong to complex numbers is an ideal in A. This is very easy. Please check this, okay? Very easy that it is a ideal. And J containing M. So this J must be equal to whole of A. Now define phi from A to C by this function rules. Any x in M and for any lambda in complex numbers, phi of x plus lambda EA equal to lambda. Please note that these elements are all elements of A, so that we define this phi in whole of A. Okay? Then clearly phi is in phi of A and the kernel of phi equal to M or M phi equal to M. It is very trivial that phi of this element equal to 0 if and only if lambda equal to 0, so that this must be, please note that x plus lambda E belong to M of phi if and only if of x plus lambda E equal to 0, and this whole if and only if lambda equal to 0, because phi of lambda E equal to lambda phi of E. This holds if and only if x plus lambda E equal to x and this belong to M. So for any M in this space, maximal ideal space, okay, we can denote this by capital M, for example, okay, denote this by M. For any M in for any M in M, we found a multiplicative linear functional on phi of A such that M equal to M of phi, so that this is a onto function, and also if M of phi equal to M of psi, then phi must be equal to psi, because In this case, phi of EA must be equal to psi of EA. Okay, so that this map is 1 to 1. Also, we have a 1 to 1 and onto function from phi of A to this maximal ideal space. And this is very important, that maximal ideal space equal to the set of all multiplication from A to C, or the set of all S. And let M be a maximal ideal dimensional one, then this quotient map is a character with this property. We have this very nice proposition. Let A be a unital algebra, then this map is a bijective from phi A to the set of all maximal ideal of codimensional 1. Dear students, we come next session. Okay, thank you and good.